Okay, thank you for the introduction. My name is Sven Linden. I'm the Deputy Head of Development at Math to Market, and I'm responsible for different solver technologies you have available in GeoDict. And today I'm going to talk about the status request or the status of different feature requests. As Ilona already mentioned, last year we had a meeting with a couple of clients, and so they prepared feature wishes, features they would like to have in GeoDict. And during that meeting, the features were presented and discussed. And today I want to give like a status update about which features may be implemented in the upcoming GeoDict version, and what is already possible with GeoDict 25, which is available today. So here you see the different features. I cannot talk about all of them today, so I will concentrate on a few of them, but I would just want to briefly mention them. So we have feature requests about to have a GeoApp to create a multi-layered structures. For example, here a fiber structure with different layers. One request was to have like more validations for the different modules. The one that you see here in the image is GeoDict, and for example, to have a better user interface for unresolved two-phase flow simulations. Other feature requests were, for example, to have an improved mesh export, to have more features and better two-phase flow simulation, to be able to simulate gas bubble transport, and also to predict the performance of fuel cells, and and 2 to 3D, but for catalyst structures. So I will talk about 4 different topics, and one other topic will be covered by the next talk by Arne Jakob. So the first feature request I want to talk about is about two-phase flow. And here the request was to have like two-phase flow simulation to compute relative permeability, but with a different slip length. So the request was to have a different slip length for the flow simulation. To shortly give an overview what a slip flow is about. On the right side, you see a velocity profile. On the top, you have a flow channel. On the bottom, you have some solid obstacle, and you have a pore solid interface. And usually, when you do flow simulations, you assume that you have no slip at the interface between pore and solid, and that means you have no flow into the solid, but also tangential to the interface, you also have zero velocity. But when you have slip flow, you can have a tangential velocity which is not zero. And usually, you use this kind of boundary condition if you have, for example, like thin gas, and if you have small pore sizes. But it seems to be also important in fuel cells. And how can that be? So on the right-hand side, you see an image from a paper. Here you see a flow channel with a water droplet, and you have airflow around this droplet, and you see that the droplet is not moving. It's stationary. So the interface is fixed, but you see that the airflow deforms the droplet a little bit. So you have different contact angles before and after the droplet. But what happens now if the airflow is fast enough, you get like a circulating flow in the water droplet. So on the right part of the image, you see like a circulating flow inside the droplet, and this leads to slip flow like a boundary condition at the interface between air and water. And what you can currently do, you can like emulate this kind of feature with GeoDict and FlowDict. So what you can do is, for example, you do a two-phase flow simulation with the capillary pressure command, and then you get a sequence of different water and air distribution. And now you're not using the relative permeability command in GeoDict, but now you go to FlowDict and you compute flow in a FlowDict. But before you do this, you can use the dilation command in a process geo, and you dilate. For the example from the slide before, you dilate from the air into the water and do then the flow simulation. And this emulates slip flow behavior between air and water, but you still have no slip between air and here in this case the fibers. So you can already do emulation of this boundary condition. What we plan to do in the next GeoDict versions to allow that you can specify different slip length for the different phases. So this we can do in the flow solver. It's not available yet, but this can be implemented, and it may be implemented in GeoDict 26. Okay, so the next feature request is about improving the mesh export. And yeah, so like the request was to have like more stable mesh export to be compatible with other simulation software like COMSOL or Ansys Fluent or Abaqus. And yeah, this is important because customers maybe already have like a software environment, and they want to use their own simulation software, but they want to use the structure generators from GeoDict. And this can be sometimes difficult because meshes can be quite big with a lot of triangles, and our software then have a hard time to import and mesh it to use their simulation. And also sometimes it also happens that with importing fails, maybe because of self-intersection of the mesh. If you do like if you do like coarsening, you can introduce errors. And yeah, so here we want to do major improvements, and this is scheduled, and we are already working on this. So in the last month, also workers started to do improvements here. So we want to improve remeshing algorithms to decrease the number of triangles, but preserve high quality meshes. And especially, and this is important where two materials touch. And so we will do more work on this to make it possible that the exported meshes are better compatible with our simulation software. Another thing we want to do is to remove the dependency from a cut look. So if you want to export a mesh in the so-called step format, you have to buy another license, a cut look license, and this makes it more complicated for the user because you need a GeoDict license and a cut look license, and yeah, not so nice. And yeah, here we want to remove this dependency and replace cut look by something else. What else I cannot tell you now, but we want to remove it and make it easier. Yeah, and of course other improvements, reducing runtime and memory and so on. So now we come to a different topic, to fuel cells again. Yeah, I think you have seen this image this morning already. So for me, the battery has similarities to batteries. So you have the anode and the cathode side. Hydrogen flows through the anode side, and some parts of it will lose its electron and travel as protons through the proton exchange membrane. And on the cathode side, it will merge together with oxygen through the oxygen reduction to water vapor. For research, it seems to be that the cathode side is more interesting because here you have water production, and water can condensate, and this makes it much more complicated. And so research happens on the cathode side. And research questions are, for example, is always enough oxygen available for the oxygen reduction equation, because the performance depends on this. How well is the water transported out of the cathode side? And what about the platinum? So the oxygen reduction happens at places where you have platinum, which is a catalyst. And how well the fuel cell performs depends on the distribution of platinum, and how does it influence the diffusion of oxygen. So what you can already do with GeoDict 25 is you can simulate the transport of oxygen and the transport of water vapor. So not water, but water vapor. Tomorrow, my colleague will give a talk about our new transport solver, which is available in GeoDict. And this solver allows to transport concentration on a given velocity field. And we can use this in combination to simulate this phenomena which happens here. So if we assume that, for example, we have air, we have just air, we have as a solvent, we have oxygen and water which stays as vapor. And if we assume we have enough of photons and electrons, and if we assume, for example, here also constant in temperature and pressure, and here we also assume that the micropores layer and the catalyst layer are not resolved, we can do the following. First, we run a flow simulation through the fuel cell, and then we use the transport solver. So we transport oxygen, and then we transport water vapor. And so we transport concentration with a velocity, and then between different time steps we use some kind of update rule, and this can be implemented in Python, and you can very easily then use a simple update rule to implement the oxygen reduction equation. And so iteratively for each time step you transport oxygen and water vapor, you do your reaction in Python, and so with that you can do like an evolution. And here in the video on the right side, you see the evolution of water vapor over time. So my colleague will give a more detailed overview about this new solver tomorrow. And using this technology, we think we can also do more. So if we have a model of a catalyst layer, we may also be able to do like a more detailed simulation, to also do maybe like a multi-scale model where we do simulation on the resolved catalyst layer and use this result for like on a simulation on a bigger scale. So okay, so the last topic will be about 2D to 3D. So as you've already heard, we have two GeoApps in GeoDict 25. With one, you can create statistical digital twins, so for fiber structures, and we have another version designed for granular structures. And we have tried it so we have tested if we can also model a catalyst layer. And here on the left side you see a 2D image of a catalyst structure. Actually, this is from another GeoApp in GeoDict to create a catalyst structure. We have used one slice of it and use the GeoApp and to test if it is possible to use it already as it is to generate a fully digital twin of a catalyst layer. And in the center you see the result. It's not ideal yet, but you can already see that it's similar. The reason why it's not yet ideal is because you have like an internal generator so you have a model, a generator model, as Eric already told, and yeah, to have like a better match between the input image. Some more work would be needed to tune it, so to change the generator model such that it is able to fit better to catalyst structures. So to do more work here, we need also like real images. So this would be like the end of the presentation. So some of the requests are hardly possible, and some are planned for future GeoDict versions. So that would be from my side. Thank you for your attention and for the discussion.